Good morning and welcome everyone to another Athena talk, Athena and Lake Mediterranean University Sci Cafe talk. It is a great pleasure and honor for us to have today a speaker from the University of Siegen from Germany, Professor Kristoph van Laerhoven. He is an expert on a very exciting topic, and we are really eager to hear about it. The topic is ubiquitous computing. And a short introduction about our today's speaker. He is a professor at the University of Siegen since 2016. He has received his PhD from the University of Lancaster in the UK in 2006 on interactive systems. And since then, he has held several postdoctoral as well as guest professor positions in uh, Technical University of Darmstadt, University of Passau, Technical University of Darmstadt as a group leader. And in 2014, he also joined the University of Freiburg in Germany as a professor for embedding systems. And as I mentioned before, since 2016, he is a professor of this exciting topic we will hear today. So thank you very much once again, Professor Kristoph, for your contribution in our Athena talks. We are very excited to hear about your topic. So I will now make you a co-host. Kristoph, host. So please share your screen and start your presentation. You have around 40 to 45 minutes, and then the remaining time we will allocate it for the Q&A session. Thank you very much.
All right, thank you very much for that very thorough introduction, George. It was very nice. So let me share the presentation, which you should see now, I hope. Right, cool. Um, so my name is indeed Kristoph van Laerhoven. I'm originally from Belgium. I'm a computer scientist, and I'm a full professor now in Siegen on a topic that is called ubiquitous computing, which may not be very familiar. So I will, in fact, also explain this topic in the beginning shortly. And it's really a mix of different type of disciplines coming together to find out what type of computing systems we will use in the future. That's more or less in a nutshell what ubiquitous systems or ubiquitous computing is about. And all of these things we will see about in, or the things that you'll see moving on the screen are topics that I will kind of lightly touch upon. Now, first a disclaimer, most of the things that I'm going to show was the hard work of my PhD students, not just from me. So this is my current team. There's quite a few people who contributed this and have finished their PhDs meanwhile and gone somewhere else in research. But as a disclaimer, this is not just my work, obviously. Now, as I promised, ubiquitous computing is a discipline that is situated within computer science. It is a rather big community of people with annual conferences that are quite large, with different conferences as well as several types of journals that focus on ubiquitous computing. And the term ubiquitous computing is not only very hard to pronounce, but also it's something that is coined by the person here on the left. This is Mark Weiser, who was leading the Xerox PARC laboratory in the 80s and 90s, so quite a long time ago, where at the time just computing was kind of personal computers, which was already a big change. So over the years, people had seen the change from computers being gigantic machines the size of a big room towards big boxes that could be put on people's desks and that were called personal computers. And he made kind of the extrapolation to say that computers in the future would become smaller and that instead of having multiple users on one computer or one user on one computer, like in the personal computer age, there would be a future where people would have lots and lots of computers to deal with, like computers that would be theirs, that they would have interfaced with, and that they would have to their advantage. And he was then at the time, so in the early 90s, making breakthrough work by prototyping these type of computers that would be commonplace in the future, he would say. So he would be, with his team as well, creating the first type of tablet computers, the first type of smart boards, the first type of smartphones. So all of those new computers that we use now daily are kind of prototyped for the first time in the 90s in his laboratory. And different things like software or adding sensors to computers were kind of started in his neck of the woods in the 90s in Silicon Valley in this laboratory. And this vision of how computing should be is still kind of actual, because at the time he said that only we people could interface with these computers if these were easy to interface with, or these would become commonplace. And therefore, he has these very famous sentences that I put here. So, computing should be as refreshing as a walk in the woods. It still isn't. So, therefore, the goal is not there yet. And one of the means that we will want to achieve this is by combining computing systems together with things like, for instance, machine learning and sensors. And that's what I'm going to talk about today a little bit more. Also in my function as speaker of the CES, which is an institute or a center here in Siegen for sensor systems, which is also supporting the Athena project, and which is also hosting the study program of Eminent, and where lots of my colleagues and myself are focusing on the next frontiers in sensing and sensor systems. So that's more or less the background of what I'm going to explain now. But what I will, of course, focus on is my own research. So my key interests in my research are somewhere on the intersection between embedded systems, machine learning, and human-computer interaction. Because all of the systems that we deal with typically center around humans, but they are, of course, also systems. And they tend to be, in my case, wearable systems. So people putting on things like a smartwatch, as you can see here, as a very early prototype that we created, looking at sensors to increase the usage of these type of devices and the intelligence of such devices, and seeing how these can be created in an efficient way, in a privacy, non-invasive way, and making sure that the user is always kept in the loop. So that's more or less the aim of my research. I see there are several people in the waiting room, but I'm afraid I can't access them. Let me see if I can enter them. No, I can't. Anyway, maybe you can do this, George, in the background. Right, so those are the things I will be talking about. So this is kind of an overview of my talk, along with some scenery from the city of Siegen. If you're not familiar with it, I see a few familiar faces in the audience that know what Siegen is or where Siegen is. But for those who have never been there, these are um, some sceneries from the city of Siegen. So my main interest for a long time already has been activity recognition. And in a nutshell, activity recognition, the way I deal with this research is by adding wearables to a person, like in this case, these two people performing a certain sports exercise. And the sensors, inertial sensors, kind of create patterns in their signals that are very unique for particular activities. So as people move and wear sensors, for instance, at their wrist or at their ankle or their torso in these cases, you will see that certain patterns emerge that always look very similar as these people do exactly these patterns again and again and again. So as people move or as people change their posture, these sensor readings change, and therefore it should be possible for a computer system to detect what these people are doing. And being able to do this is very interesting from multiple perspectives. For instance, looking at sports. So this is one area where we have been quite active in looking at detecting sports exercises automatically. And if you look at this person on the right who was doing particular exercises for a martial arts sports, we could look here at the sensor data from both the wrists, the torso, and the legs. And you can see here that for the leg signals, there's a lot more happening than for the other two sensors. And the sensors are inertial sensors or accelerometers. They sense things in 3D. And as you can see that for the leg, there are big peaks happening. So you could, for instance, probably already look at this data and say this person is probably kicking because the leg is showing huge peaks in the signal. And you could see even how often this person is doing this because the pattern for a single kick can be seen quite nicely as well. So you can see that this person in this case is kicking 5 times. And by looking at this pattern and doing pattern analysis or machine learning, you could even detect what type of kick this is. You know, a kick where the person at the end is, for instance, turning slightly their foot to the left, which is then, for instance, one particular type of kick in this martial arts sport. As well, what is also possible is you can take all this data from the wrist, from the torso, and the leg, and try not only to predict what this person is doing, but also how often and also how well this person is doing this activity. So whether this is a black belt martial arts expert, or whether it's a novice, beginner, or somebody who is in the middle of their training, for instance. So activity recognition can tell you lots of things about the person wearing these devices. And meanwhile, these wearables have been marketed as something that people can buy for not that much money. And therefore, these things are very ubiquitous, very pervasive around the world. People, from children to elderly people, tend to wear fitness trackers, smartwatches, etc., that can do exactly these type of things. Sense what the person is doing at exactly which time. And this is still an ongoing piece of research, but of course you will see here applications that already exist, for instance, for tracking fitness. Now we started, or I started this in the early 2000s. And then, as George already said in his introduction, I started at the Technical University of Darmstadt, my own team, my own research team, through funding from the German Research Foundation called the Eminöter program, which would allow people to start their own small research group with 2 PhD students and a bit of starting funding. So that's how I started to create this particular type of research, where me and 2 others, or 2 PhD students, started creating a system that had the looks of a smartwatch at a time when there were no smartwatches yet. So this was 2009, 2010. So we had to prototype our own smartwatch first. So we created these prototypes of a smartwatch which tell people the time and which would allow us to record this type of acceleration data, this inertial data, as well as temperature, light, and several other sensors over the course of a lengthy period typically. Since we created these devices ourselves, we could do this very efficiently, and typically people would have to recharge their battery only every 2 to 3 weeks. And they could wear this watch, or they should wear this watch for multiple studies, day and night. So the data that you can see here at the top right is from over a couple of days, and you can see here that during the night people don't move too much. They shift, their position on how they're sleeping. So you can see in the accelerometer data that you can see certain things there. But then during the day, there's a lot more motion. There's a lot more light, as you can see in the yellow bars. That's the light sensor. You can look at also the temperature on the skin. Also, that typically is higher during the day than during the night. And that way we can kind of look at multiple aspects of the user, whether this user is sleeping, whether this user is sleeping well, for instance, if they have these twitches during sleeping that can tell something about which sleeping phase these people are in. Also, there we did quite a lot of research with sleeping laboratories. During the day, we could also do very basic gesture detection. So it turns out that when you're smoking, this is something that can be characterized quite well as long as you're smoking with your dominant hand and the sensor is worn on the dominant hand. So if you're smoking with this particular hand where the sensor is being worn, then this gesture of bringing the cigarette to your mouth and putting it away again is so characteristic and in time so constrained. Typically, smoking a cigarette is about 8 minutes. Um, that this can be characterized really well and also detected in the data. And beyond these gestures, our interest was mostly in very complex activities, like, for instance, playing tennis. And we called this at the time leisure activities because in psychiatry, leisure activities are kind of key pieces of information that psychiatrists and psychologists use to see for particular patients whether they are, for instance, heading for a phase that could be a depressive phase or depression, or a manic phase, for instance, where they become very manic. So typically, the leisure activities, and for instance, for depression, start to getting less and less. People don't do their leisure activities anymore, or hardly, or not anymore at all. Whereas if you go for bipolar patients, where patients really go towards a manic phase, they start doing these leisure activities for a very lengthy period. So they play tennis for half a day or an entire day, even sometimes, or they start pacing a lot. So also these type of activities people would like to recognize. That's something we did in this work, in this early work, where we try to prototype a smartwatch that just records data, and also it tells the time. And from this data, we try to automatically recognize what the person was doing throughout these weeks when these studies were ongoing. So this was 10 years ago, or about 10 years ago. And since then, we learned a lot about what we can do with this type of data. And now, just shifting towards now, what this research looks like at this point in time, is we're doing still this type of research with extra material, with extra sensors. For instance, egocentric camera sensors. So you probably know that there's now quite a lot of smart glasses, wearable types that you can also wear, put easily on your face or behind your ear or in your ear even, which sometimes are also equipped with cameras. And from the cameras, we have a little bit more information from the sensor data, because camera data can be interpreted later on. The signals you saw earlier are time series that are very hard to interpret by any person. But I think if I show you any of these videos, then people can typically tell what type of exercise these people are doing. So this is kind of the thing that we started now, and where we created a sports data set that just was published a month ago, where 22 people from a variety of courses of life were serving as volunteers and did a series of activities for us. Usually about 2 minutes each session for 18 workout activities, as well as a background activity where they were not doing any of these 18 workout activities. And this under a variety of conditions. So in different locations, different seasons, somewhere in the winter, somewhere in spring, somewhere in autumn. Um, and for loads of different types of activities. And of course, we just not looked at the camera data, but also at the data from the typical IMU sensors that you see here. So we added for each wrist and each ankle, the data that you already know, that we've already seen from accelerometer data. And then we have them the knowledge of what a person was doing. In this case, this person is doing burpees. And you have also the egocentric data from this person. And this is kind of exactly the same type of data set that you saw earlier. It's going for not days and weeks, but it's a bit more short term, but therefore also a little bit more well maintained. And people can use this to kind of use as a benchmark data set to test how well particular machine learning classifiers tend to work on this data. So this is now open. Everyone can download this. We're working on tools to visualize this data as well. And many people have already used this data set to look at new ways of doing activity recognition. So of course you can take just the right hand, which is usually where people wear these fitness trackers, but there are also anklets that people can put in their shoe, on their shoe, or wear on their anklet, for instance. So you can look also at this data from the feet. So this is something that is out there that we just created and which we are now extending as well. Now, with these inertial sensors, you can do quite a lot. And this is another strength or part of our team, I think, because we have kind of a good vision of what these systems can do. And accelerations that you saw earlier are just one out of three types of sensors that people typically have in a so-called inertial measurement unit. And I think also for those that are studying eminence, it's important as a MEMS type of system, because it's like a success story on how small you can create sensors. This inertial measurement units started as single axis accelerometers used for airbag deployment in cars. But meanwhile, it is integrated in every type of wearable and every type of device that you can imagine because they have become so small and so cost effective. So single accelerometers are kind of working like what you see over here. So you have like a tube in which you have a little ball with a certain mass that is attached to two springs. And as you enter, or if you as you shake, for instance, this tube along its axis, this acceleration is measured that you inhibit to this. This is not really how they are implemented. Usually, it's a cantilever methods, but you can easily reason with accelerometers like thinking in this model. So that's way the position of the ball inside this tube is kind of the measurement that you're doing. And that you're doing in 3D. So you have three of those at 90 degrees angles amongst them. Now, these accelerometers are great, but they have a weakness because if you would take this 3D accelerometer and you would turn it along its axis perpendicular to the Earth's gravity field, you would not be able to measure any motion there. So because of that, people add to the 3D accelerometers, typically also 3D gyroscopes, and to also get them the direction, people also add a 3D compass. And that's typically an inertial measurement unit. It's nine sensors combined into one into a chip package that is about 1 millimeter in diameter. So it's really, really tiny. And that's what the breakthrough has or has been since the last decade. People or companies like Bosch, for instance, create these type of sensors at such a small scale, at such a large amount that these things have become really cheap and really mass produced. So these combine loads of sensors, typically also along with temperature and humidity sensors to calibrate these, and they deliver really good um, uh, uh, output. Meaning, this output is kind of the way the thing that this IMU is attached to is moving. So if this is worn on the wrist, you can really nicely track how this person is moving in 3D. If this is attached to something else, like an object, or it's also used a lot in drones, for instance, to stabilize drones. These IMUs perform meanwhile or output something that is really, really well. And this is usually in a quaternion, which gives also orientation in a more or less perfect way. And a quaternion is kind of a 4D vector, which does more or less the same as the typical orientation vector that you might be used to with roll, pitch, yaw, or Euler angles, but it has or solves a couple of issues that those have. So typically quaternions can be directly gotten from these chips, and it can be therefore or giving you automatically the direction of something that the IMU is attached to. And this can be used, for instance, in looking at wearable data. So you can see if you wear something on the wrist, you can kind of track the person's wrist and therefore the entire lower arm. And you could, for instance, wear this wearable not just on the lower arm, but also the upper arm, or the leg, or the torso, or the head. So you could wear this wearable IMU anywhere. Now, we asked ourselves, what if you would do sensing from two perspectives? From a camera, and I think most of you are aware that you can detect a person's posture from a camera really well nowadays. There are packages out there like Google's MediaPipe, where these are automatically created in real time from simple cameras that are, for instance, embedded into your phones. And that is one way to getting the posture of every body segment of a person, but you can also let them wear a wearable IMU. And you can try to combine this and see, for instance, for a given sensor, where this who this the person is that is wearing the sensor, as well as where. So that's what we're going to do now in a study. So at the right over here, you have this output, this quaternion output of our wearable IMU. On the left, you have people trying to do synchronously the same type of movements. And then we try to see if we can get an algorithm to detect on which person and where this person is wearing this particular wearable, right? So we kind of start by having then lots of people, in this case, three people, doing exactly the same movements. They dance, for instance, they walk, and they try to do this in exactly the same fashion. So it should be really hard for an algorithm to detect the outcome of the wearable, the output of the wearable, and to which segment this is belonging to. Well, it turns out that it's very easy. So usually within a couple of seconds, we can create like a matching algorithm that looks at the output, the quaternion output of these wearables, and matches it to the body posture segments from a particular camera that is looking at different people. So we can find who is wearing this, and we can also find where this person is wearing this particular wearable from looking at both angles. Now, another thing that we do typically in our research is looking at the time series or the signals that these sensors provide. And therefore, we use very classic algorithms and try to use those for newer type of sensors. And this is one example how we can do this. So one basic algorithm that is well known in data mining is called sliding window. So basically, you look at all the data that a sensor is providing you. Those are the red diamonds that you see here. So for every couple of milliseconds, for instance, you have a new piece of data. And you try to approximate this data by much less data. And this is kind of what gives you the sliding window approach. So you start with these blue linear approximations of the data, and you try to approximate in such a way that instead of having all these red diamonds on the left, you can approximate this with the blue lines, which are kind of a compression. You try to compress the signal in such a way that it only is showing just the basics of the signal, the elementary parts of your data. And the sliding window goes from left to right, and it's very easy. So as soon as you grow this linear segment, this blue segment, you keep the left parts fixed, and the right part, you go to the next point each time. And you see how well this approximates all the points along the way. So if these green lines are becoming too big, then your approximation cost is too high. And if it is becoming too high, like in the second example here, you go one step back and say, now the blue line that we had is the optimal, and we start with a new blue line. So we start from the right point of this blue line with a new one. And that way we can kind of approximate our signal with a few linear segments that sometimes compress the signal a lot. Like in this case, when I go for the next line, I will have dozens of data points captured by one single blue line. And this typically is a very good way of looking at the essence of a signal in time. Turns out this sliding window approach is pretty good already, but there are better ones. For instance, one of the better ones is the sliding window and bottom-up approach by Im Keok at UC Irvine. So he looked at a sliding window over time, which makes this algorithm a lot faster. So there is a bit of a constraint here, but this is typically not a problem. And this constraint allows us to get the best segments inside this window and slide this along with the sliding window approach, which gives you a much better approximation of the signal itself. And at the same time, also guarantees that it can be executed, for instance, in a very small computing architecture like a microcontroller. So this is one approach that we used, that we specified for particular sensors, and where we use this to optimize the signal. So we don't have to keep the raw data anymore. We basically have these linear segments which show exactly the same type of signal than the raw signal that we digitally got from the sensor. And this we can, for instance, use for quaternions that I just told you about. So these wearable quaternions from wearable sensors, we can take the quaternions coming from a camera, which estimates these from the posture of the person's joints, so to say. And we can take the original data and compress these with such algorithms into linear components. So basically from the original data, which you see at the top left, we kind of compress this, for instance, with PLA, with different types of things like sliding window, fast sliding window, which is our approach. And the data points that you see there are basically the linear segments anchor points. So those are the points you keep, the rest you kind of can throw away. And that leads to a massive compression. So I see you then, for instance, try on a data set. This is a well-known data set of actors performing certain movements or actions. And you can look at if you compress from the 100% data to all the way to 10% or 5% or 1% of the data, you will see how those movements still might be the same, but you compress the data to a tenth of the original data or to a 20th of the original data for 5%. And if I now start this video, you'll see that even up to 10% or 5%, these movements are very, very similar. 1%, so reducing it to one hundredth of the data tends not to work so well, but it allows us to compress the signal a lot. And this, of course, is useful for instance, wirelessly um, sending this data, if this is a wearable, or also, for instance, to create data sets that are much smaller than the original raw data. Right. A next study part that I went into, as well as activity recognition, is in effect recognition. And effect recognition is doing more or less the same, but with not just accelerometer data, but with lots of other types of data as well. So this is part of a data set that we collected 6 to 7 years ago, called WeSat. It's a piece of work that many people are now using as a benchmark data set, and where we followed 15 participants over an entire afternoon, where they went through different phases that we kind of constructed ourselves as the experimenters, and where people, for instance, for the amusement phase, looked at funny videos, or for the stress phase, had to present themselves to the bosses in the company, and had to do an impromptu, spontaneous presentation, or where they went through meditation phases. So we would create stress, we would create amusement, we would create a meditation effects phase for these people so that they would go through these phases. Along this, at every black bar that you can see there, they would have some breaks. And during the breaks, they would have to fill in questionnaires that are known from psychology. So from that questionnaire, we hope to then get the feedback that yes, they were stressed, our stressful phase. Or yes, they were amused when they were coming from an amusement phase. And at the same time, we did also regularly saliva tests. So they would have to get these samples that we would analyze later for cortisol. So we would also measure stress levels during this study. So that's what we measured, and that's how we kind of constructed the study so that people went through these phases. And now the sensing part, we basically let them wear both types of sensors. On the left, you have a single wrist-worn sensor. It's an Empatica E4, which some people might know. This is kind of an early prototype of a smart watch that also kind of has interesting vital signs, such as the conductivity of the skin, or PPG, like photoplethysmography, so heart rates can be detected with that. But it does this in a very easy and comfortable way. So donning this sensor, wearing this is very easy. On the right side, people also had to wear this medical grade system. So on their chest, they would be collecting very similar data to the smartwatch, but at a much higher rate. At 600 times per second, you get all the data from electrocardiograms, from breathing, from skin temperature, etc. Similar sensors as the one on the left, but much more fine-grained, much more frequent, medical grades, basically. Now, it turns out if you take the data from these two type of systems and you try to detect the affect state of these people as we went or as we created them for these participants, it turns out that if you take the data from the left, it is not much worse than the data from the system on the right. So you lose a few percent if you take all the data. That's what I marked there as the purple bar, so to say. So for detecting stress versus non-stress, it would be having an accuracy of 88.33% for the smartwatch-like system. For the medical grade system, you gain a few percent, so it's 93%, but this is not much. Knowing that the participants had to kind of often shave, but also had to don this big system, and this would be very hard to wear for a longer period of time. So the entire afternoon that these people had to wear the system was already quite, asking them quite a lot. And if you, for instance, want to detect stress versus amusement versus the baseline affect state of these people, you would also lose a bit of percentage accuracy in what you can recognize out of the sensor data. So there you would have only 76% with a smartwatch and 80% with the medical grade system, but also that is still quite good. So we got from this study that actually the smartwatch-like system gives us much less fine-grained data, but this is still pretty good to detect the affective state of these people in our WeSat datasets. Now, this we followed up with a study in the wild where people had to wear exactly this smartwatch over the entire day for about 2 weeks. So we took completely new people, 11 people, that were monitored about 2 weeks using exactly the same smartwatch. In this case, not the wearable medical grade setup, because that would be just too hard for people to wear. And we would try to see what affective states people went through. The hard part here is that we can't dictate whether people go into a stress situation or people go into an amusement situation. So we would have to get this information from the people themselves. And for that, we used a custom smartphone application to kind of try to figure this out using techniques from psychology. These are called ecological momentary assessments, EMAs, which we use to kind of get the affective states over the time next to the sensors. And we try to recognize, just like in the previous study, how well we can do this with these sensors. Turns out, with something that was performing the best at the time, with a CNN-based deep learning network, and trying to predict the outcome of questionnaires, psychological questionnaires, that our performance was much worse. So here are, the bars here are for different types of classifiers. On the right is basically the CNN-based classifier that I just showed you. But instead of having a performance of 70 or 80%, we would have a performance of, or an F1 score in this case, but it is very similar, of less than 50%, so 45%. This is still okay as a predictor, but it's of course much worse than for our earlier study in a controlled environment. And that is the problem that we face now. Whenever you want to test wearables in a laboratory environment, you typically get very good values, like you saw earlier, 70, 80, 90% for both effect recognition as well as activity recognition. However, if you let people then go through their normal lives, you probably have the problem, first of all, that you don't really know for sure that these people are doing exactly that what you think they are doing. So you can't really test that. And that is one of the problems that we call the curse of normality. Typically, people during their daily lives are doing things that are not that important for these classifiers. So they are not very stressed or they're not very amused. Or for activity recognition, they're not doing burpees all the time, right? So in that case, these activities tend to happen only now and then, and we would need to have loads of information, lots of capturing of data to kind of counterbalance this. And I think this is one of the problems that we are facing currently. We have some ways to mitigate this, but this is, I think, one of the problems that we work on. And then I want to finally finish with some cutting edge themes that we're working on now, which go in a slightly different direction, but we kind of show, I think, a very similar framework in terms of what we can do. The first one is that we created the similar systems, with IMUs, but for much more fine-grained articulation of what we want to track. For instance, the single hand or fingers of a hand. We want to accurately track this, not with a camera, but with IMUs. So we created this kind of like wearable which you can tape to your fingers, which you can wear, and then, for instance, play the piano. And then we can try to see whether we can reconstruct that piano piece by just this data. So not with camera data, not with capturing the piano and the person's hands, but with just the IMUs on the fingertips, along with the IMUs on the back of the hand, along with the IMUs of the wrists, with which you can basically reconstruct the entire lower arm and hands. So that's one of the things we're currently doing, and which is what I'm interested in, as well as trying to look at different modalities. So looking at the vision modality, also look at eye trackers, so people can also wear eye trackers, meanwhile, which also are interesting pieces of information. So you see what people are interested in or focusing on, as well as trying to capture the entire environment so that people then, for instance, can help us understand the world while we are sensing the world. We can understand from the vision whether they are looking at a kettle or a cup. We can look at the motion data, whether they are taking the kettle and pouring the water into the cup, for instance. And from the wearer, we hope we can listen in as the wearer is saying, look, I'm now making tea by taking the kettle and pouring hot water in a cup in my kitchen, for instance. So we can also look at what is happening there. This is typically now already done in computer vision, but we want to extend this to the many more modalities that a wearable can contain. So that is also one of the hot topics I think that is upcoming in this type of sensor-based research. Right, with that, I'm at the end of my presentation. I thank you for your attention. If you have questions, these are, we can of course answer them straight away here, but these are ways to contact me and feel free to do so. Thank you very much.
Thank you very much, Professor Kristoph, for this very nice and informative presentation. So the lecture is now open for Q&A. I see Samuel with a hand raised. Yes, please.
Yeah, you hear me?
Yes, we can.
Yes.
Okay. Thank you very much on a very interesting presentation. And I want to ask you a question. How Ubiquitous computing method can support effective face different disasters and emergency situations?
Okay, I'm not entirely sure if I got the entire question, but I understood emergency situations. And what type of sensors were you? Face recognition, I think this is what you said, or
And disasters. And disasters.
in disasters? Yes, and what sensors were you talking about?
Yeah, disasters, different disasters of
Okay, so the sensors that we are
different
basically building.
natural disasters, wars, and another disaster.
Okay, understood. So basically, yes, you could do this most likely. Um, we have not done this because this is, of course, I mean, typically, I think this is a very interesting question because it kind of highlights how the community is valuing benchmark data sets. And of course, in these data sets, we need to record something that we can easily control. And natural disasters are very unique experiences that you can't control or simulate probably very hard. So this is typically not really done in our community, unfortunately. Um, However, on the other side, there are lots of projects of colleagues, mostly of myself, that have looked at this. So that basically, for instance, look at staff, emergency workers like firemen and firewomen walking through a disaster area, and then, for instance, beaming their activities to a control station, so that people that are in the headquarters or in the control room can see in which position, where, but also in which condition people are, for instance. So these are research projects that have gone underway, that people have done, and that show kind of what is possible also with activity recognition, not just as a medical tool, because also there's lots of medical projects in this area, but also as in a way of conveying what a person is doing inside an entire team. So also that is something that indeed is happening in research.
Thank you very much, Samuel, for
Thank
the
you very much.
question and Professor for the answer. Now I would like to give the floor to Christina, one of our talented master students within the Eminent program. So please, Christina.
Yes, hi, Professor. Thank you for your presentation. I have a question, first of all, regarding possible applications. So are we talking here about, I don't know, gesture language recognition or like help in rehabilitation? So this is one question. And then the second is, how, excuse me, how your device is better among others. So for example, we could use for gesture recognition or like movement recognition, some Kinect camera. Like, why would we use, okay, I understand we cannot use it everywhere, but still it's kind of cheap. It can be cheap and really useful in medicine. So yes, why wearables?
Yes, that's an excellent question. So, for instance, a former PhD student of mine was embedded in the university hospital in Freiburg, where he monitored hundreds of epilepsy patients. And there, the activity that we want to detect was epilepsy seizures or epileptic seizures. So there, it's really about the detection of an epileptic seizure, which can be done indeed with cameras. And the way medicine is doing this nowadays for very serious cases is that these patients stay or have to stay in their room in the hospital. They're bound to their beds. They're constantly observed via EEG, so they have this basically helmet on. In the room, there are cameras filming the patients. There's also audio to make sure that the medical staff can capture whenever a seizure is happening. And this would be the traditional way indeed to do this with a camera. Um, the need, however, for wearable sensors was from this medical staff because, of course, this is usually not during very naturalistic environments. It typically happens also for many patients that they have very frequent seizures during their daily lives. Then they come to the hospital, there they stay for weeks, and they don't have any seizure because they're observed by people and they're uh, taken care of. So to find out when these seizures, these actions are happening in daily life is something where you would need sensors that are following the person at all times. And that is I think, a good example of where you can't use cameras or depth cameras or audio in the environment that looks at the person. You would need to have a drone following you to have very similar type of information. But of course, it's the case that for other things, like a patient comes to a doctor and you want to examine this patient only then of course, sensors that the doctor has in their office would be a lot better than wearable sensors. So I think there's a best world for both type of sensors. Typically, I would say wearable sensors are for monitoring things in daily life where you can't install sensors in the person's environment. Whereas if you go for a well-described situation, like a visit at a doctor, there you can actually put a camera next to the doctor and film the patients. I mean, typically there's also problems there with privacy constraints and these type of things, but obviously the sensors would be much better suited there. So I completely agree there that there a depth camera like a Kinect or an RealSense or whatever would work really well there as well and would be able to indeed capture probably a lot more information than from just the one wearable that a person would wear. So there's conditions in which you would use one and use the other system, I would say there.
Okay, thank you for your answer.
You're
Thank you,
welcome.
Christina, for the question and Professor for the answer. Is there any other question or comment? I see, George, you switched on your camera. Would you like to ask something?
No, I'm fine. It was very interesting. Thank you.
Okay.
Thank you.
So maybe we have 3 more minutes. I may have some more general question, like what do you think should be, what type of advancements are needed for software to realize the full potential of this kind of topic, ubiquitous computing? And also my second one is how the recent progress in quantum computing or, for example, machine learning can be utilized from this kind of topic. Thank you.
All right, thank you for that question. So to start with the latter part, I'm not entirely sure how quantum computing could improve things here. I know that some people are working on making algorithms more efficient through quantum algorithms, so that would be perhaps one way, but I'm not an expert on that. So I'm I think I won't be able to answer that. But machine learning, obviously. Also in machine learning, I think we can definitely improve the algorithms on many fronts. And I think that's also where current weaknesses are. I think in terms of software, it's not just about which classifier you use. That is one thing you could, of course, investigate, but I'm pretty sure there we are already quite well advanced. And also there, the community of the tens or hundreds of thousands of people that look at activity recognition or action recognition in computer vision know quite well what to do when. It's basically, I think the problem is also dynamically, for instance, adding to these models. So if you have a machine learning algorithm, you feed it data, and then typically from this data, a model is constructed that then is able to detect when people are doing what. However, in most situations, it doesn't always work well because there's no generic way of doing one particular activity. And then you want to, for instance, retrain this. And that is something that we don't really know well yet how to do, I would say. So these are kind of like semi-supervised learning or unsupervised learning type of methods where these systems allow the user to say, no, actually, I was not doing this, I was doing that. And then the system listens and can adapt itself yet again. So this would be kind of more like an active learning approach. There's multiple ways to approach this, but I think building this into a system is something that is not done yet. And another thing that is quite important is also wirelessly connecting all of these sensors to be able to build a very potent model that can detect all of this. So also there, typically people focus on just cameras or just depth cameras or just audio or just inertial sensing. But I think the power of this lies into combining all of these sensors together. Also, that is not entirely used yet. I think also there's loads of potential for people to make advances in both of letting this sensor data come together as well as in using this data.
Thank you so much for the very detailed and insightful response. And let me check the chat as well, if there is any additional comment. It doesn't look like. So, if there is no other additional comment or question to the speaker, I would like to thank you, Professor, once more for your contribution. Very interesting and very, let's say, promising topic for future development in engineering. And thank you also very much for everyone for participating. And before we close, I would like to announce next week's topic, which is again from the University of Siegen, Professor Peter Kramer, and the topic will be mechanics with a focus on structural health monitoring. So, thank you all, and speak to you soon. Take care. Bye.
Thank you. Bye-bye.
Bye.
Bye.